Okay. Good evening, everyone. So we,
Good evening, ma'am.
hello, sir. So now we will start the discussion for today. So this is Adyasha Sahoo from Electrical Engineering Department, IIT Roorkee, and today we'll be discussing the course content of week 7. So this is how the presentation is going to flow. We'll see the overview, the key concepts for this week, followed by the Q&A session and your doubts. These are some important links if you want to access the PPTs and videos for this lecture. Then, okay, so this week we started with the control of various AC microgrid, DC microgrid, and then AC-DC microgrid. So first, let us see why at all we need to control this microgrid parameters. So firstly, it is obviously for the grid resiliency purposes. So what it means is because as we know the microgrid it can operate in both grid connected as well as islanded modes of operation. So for that transition from one mode to other mode we need to switch in the controlling strategy also. So for that we need to control the microgrid parameters. Then obviously for reliability, because our microgrid is consisting of various numerous distributed generations such as solar, PV, renewables. But with this also we need support from the grid in case of any mismatch between the generation and demand. So for that, then obviously energy efficiency with the improved control, what we can have is basically we can minimize the losses and we can prioritize which critical loads we have to supply. So those all things can lead to efficiency in terms of energy. Then grid integration, obviously it will help to integrate the renewables. Basically when we will be having excess amount of energy we can feed into the grid, and whenever there is power deficit we can take support from the main grid. Load management, obviously with the help of microgrid control we can prioritize, as I said, let's say we have limited generation capabilities, then which load we need to satisfy. So basically we need to satisfy the critical loads such as hospitals, military bases, then airports. So for that strategy we need to have proper control strategies. Then these all points we saw, also renewable integration obviously, then grid support in terms of various ancillary service. Basically these distributed generators, they can provide various voltage related services or frequency related services. So for that we need control strategies. Then energy cost management, that is power cost management basically. So we can optimize what amount of power we want from the grid at what amount of time period. Then environmental benefits, because this microgrid control can help to integrate more amount of renewables, so that in terms will reflect in the growth of these green resources, and hence we'll be having environmental benefits from here. Then of course we have scalability here, because as the number of applications will increase, so in those cases we can say scalability can be increased here. So the first what we saw in the introduction was the hierarchical control. So basically we'll start from the lowermost one. So what we had in the lowermost was, that is the starting control layer we can say. So local control layer basically. So here it is operating in decentralized fashion. Basically we are not communicating with others here, decentralized, and we are just the inverter control whatever has been fed in the inverters, only that control action is taken here in the local control layer. Then followed by secondary control layer. So because this local control layer is not aware of the we can say global objective, since there is no communication here, it is decentralized, so it may not be able to achieve the global target. Since it is not aware of the global target, we may not, there is no communication, so there may be deviations, it may not be optimal. So the secondary control layer will build upon the local controller to match the global objectives, we can say global objective or global target basically. Then after this we have our central controller. This is the topmost in the hierarchy, and it is used for communication we can say between the microgrids or between the distribution system operator. So basically this is the hierarchy we are following here. So I'll just say once again. So this is the lowermost local controller close to the distributed generators. So it is involving only the inverters here, and they are not communicating with each other. They are just blindly following some control algorithm, whatever has been fed in the inverters, they are acting upon those only. But since they don't know of the global objective, the secondary control layer then again will improve the performance of the local control layer, and it will try to match the target, global target. So this is the secondary control layer, and then above that we have the central here, central or emerging controls, which is within the microgrid or with other microgrids or with the distribution system operator, that we'll see. So basically here we have different microgrids within a distribution system, we can say. So as you see in the hierarchy, what is happening at the bottommost layer, we are having one microgrid operator, and we can say what will be its responsibility of the microgrid operator. It will look after the network constraints, I mean voltage limit, power flow limit, line limits, as you can say, basically whatever hardware components that comes under its area microgrid. So it will look after those network constraints, plus it is also responsible for also the power mismatch and participate in the market to meet this power mismatch in the in the own microgrid. So basically we can say, let's say our microgrid is containing two PVs and one wind. So these PVs and winds, wind generator basically, they will communicate what at the instant what amount of power they are producing. So depending upon the power that is being injected by these renewables, the microgrid operator will, what it will do, it will calculate the mismatch if it is there, and it will also look after if any network constraints are being violated, and the mismatch that it is having, it will then try to accommodate with the a distribution system. Basically, it in the microgrid, and similarly, what will be the distribution system do? Here we will be having, we can say the various microgrid, we can say 1 to n, they will report their mismatches, power mismatches, to the distribution system operator. Then what the distribution system will do, it will take 1 to n, basically I'm writing here, considering the power demand from these microgrids 1 to n and looking after the network constraints of its distribution system, it will then calculate the power mismatch, basically power mismatch, and it will participate in the, it will basically clear, we can say it will clear the distribution system market, and the mismatch, for that mismatch it can participate in the transmission level market. And what are the responsibility of the TSO? Similar to that, it is responsible for the operating its own network constraints, we can say, in transmission system. And here we will see that it will clear the transmission system market considering the demand from n number of DSOs. So this is the hierarchy. So single microgrids, they will first look after their grid, then any mismatch they are all going to report to the distribution system. Then the distribution system, considering its own loads and also the demand from the microgrid, it will clear the distribution system level market here, and then it will report any mismatch, like if it wants to export energy to the transmission system or it wants to import from. So that information, again n number of DSOs present in the transmission system, they will report to the transmission system operator, and finally in this transmission system level market, these all we can say schedule or dispatch will be finalized. So in the first we'll discuss about the local hierarchical control. So firstly we saw here group control, right? So as we see, this is the plot between frequency versus power, and let's say initially it was operating at a frequency f naught, then the generators, generator 1 and generator 2, they were producing power P1 naught and P2 naught. Then again after this at frequency f naught, let's say there is an increase in load, so that the frequency will drop, there is a drop in frequency here, then this additional amount of power they have to supply, but who will provide how much amount of power will depend upon this constant k that we'll be discussing here. So basically if we see here, so this f naught minus f, let's say we are writing for generator 1, so f naught minus f will be P1 minus P1 naught, that will be equal to Kp1. Is it fine? Then similarly if I, so this was for the first one, then if I write for the second generator, basically it was P, okay, and here we can say. P1 so what we will be having here is P2 minus P2 naught, and here this will change to Kp2, right? So from both this, what we can, if we equate this F naught minus F is same, right? So if we equate again here, what we'll be getting? So basically Kp1 times P1 minus P10 is equal to Kp2 times P2 minus P20. So if we write here this as delta P1 and delta P2, what we'll be getting here is delta P1 by delta P2. I'll erase it. Right, I think this one relation we had seen in the lecture. So the power that they will be sharing, basically this ratio delta P1 delta P2 is depending upon this coefficient Kp1 and Kp2. So basically we can say this delta P1 plus delta P2 should be the new load demand, PL dash we can say. So again let's derive something. So initially we had P1 naught plus P2 naught It was the initial condition where the load was PL. Then let's say we had an increase in load. So now the generator outputs are P1 and P2, and that is equal to a new load PL dash. So basically the change or the increase in load delta times, we can say PL, that should be the increase in individual generators output, right? And from the equation we had seen that delta P1 by delta P2 was Kp2 upon Kp1. So but from here what I can do, if I want, then I'll take it here. So basically delta PL and let's say delta P1 is as it is, and delta P2, let's say we replace from this equation. So what will be delta P2 in terms of delta P1? Delta P2 will be, let's say I'm dropping this P, it will confuse only. So P2 will be K1 K2 times delta P1. So from here what will get delta P1? It will be delta PL divided by 1 plus, let's say this K1 plus K2 I am saying as R, that will be 1 plus R. And what will be delta P2? So we had seen here, from here delta P2 was K1 K2 times P1, and delta P1 we had replaced by, so if we replace here basically we'll be getting it as R plus 1 plus R times delta PL. So finally what we get is this one delta P1 and this one as delta P2. So if you know this coefficients, group coefficients basically, and you know how much change in load you want, you can calculate the load shared by each generator using this relation. But this group control, it is again having some drawbacks. So what drawbacks? Firstly, inaccurate voltage regulation, because here only we saw the power sharing, but similar group control you can also have between reactive power and voltage. And if you do the group control for reactive power voltage control, it will give you inaccuracy, because this inherently involves estimate, it will depend upon the line impedance basically. So due to this reason basically you won't get proper voltage regulation. Although the power sharing is perfect for this group control, the voltage sharing is not accurate, you can say. So this is the challenge here, and obviously it will also provide limited reactive power control. So inaccuracies in voltage regulation means there is no sufficient reactive power support. So basically, you need to add other reactive power support devices such as capacitor banks or other reactive power sources for voltage stability. And it will also possess a synchronizing challenge, because while synchronizing this, you need to precisely match this droop characteristics so that this delta P1 and delta P2 you get equal. For that, what you need to is you need to match this K1 and K2. So to improve this droop method, we are using some methods here. Firstly is the virtual impedance based method. So here we are additionally adding a fictitious resistance, we can say, which will act, or which it will emulate, we can say, the performance of the line resistance, and then it can help to overcome the inaccuracies due to this. Then there is adaptive droop control. Basically, we saw the droop characteristics this way, let's say for QV. So in adaptive droop control, what we do, we change this droop characteristics. So I'll give example in the one such droop characteristics that we use for QV. So basically this is your Q. So what we do here is we modify this droop characteristics as this way. Let's say this point is voltage 1 per unit, and let's say this point is, let's say, voltage 0.9, not 0.9, it will be greater than 1 basically. Let's say this is 1.5 and this is 0.95. So you know that we need to maintain the voltage between certain band, that is 0.9 to 1.1 per unit. So what we do this in adaptive droop is when the voltage, no, actually I did it slight modification. So this will be here this way only, but then we'll be having a, you can see, let me erase this whole thing. So we'll have a dead band here, and let me get this as 0.98, and let's say this is 1.02. So within this band we see that the voltage is acceptable, because the voltage cannot be at dot 1 per unit always. So we see this is acceptable to for us. So we don't want any Q support. Basically here it is Q. We don't want any Q support from the grid. So during this phase, when the voltage is between 0.98 to 1, we are not taking any Q support. But as soon as the voltage will decrease from this range basically, and this is the Q max, and you can say this is the Q min or negative of Q max, and let's say this point is 0.95. So as soon as the voltage will drop below 0.95, or it will increase below 1.05, basically this region here. Here what we are doing is we are injecting the Q according to this droop slope, right? And when the voltage is below here 0.95 or greater than 0.05, so the voltage situation is alarming. So what we are doing, we are injecting whatever Q we have having, whatever maximum Q support we are having, we are providing during these crucial periods here, during this alert states. Basically we are giving our maximum Q support. So this is one such method of adaptive truth control. There are also different ways of like different ways of plotting this, like changing these characteristics. Then similarly, angle droop control, like this was between Q and V. Similarly, you can do between P and F. Then virtual frame transformation, what we do is we are having ABC frame. What we do, we then transform those ABC frame quantities to DQ frame. Then a virtual inertia based loop control. What we do here is, since we know that the inverter based resources, they are, we can say, low inertia devices. So any change in power, little, if P changes by some quantity, let's say delta x, the frequency is going to vary drastically. So what we do here is, in virtual inertia droop control, we increase the inertia so that for minor changes in power, the frequency does not shoot up. So this is what we are doing here. Then say this local control we completed. After this we had secondary control. So basically the main objective here, we need to give the optimal dispatch, or that P star Q star, to the distributed resources. And also the disadvantage that we saw in the droop control, that since it is localized, as I said in the previous, so what may happen is, it is not knowing that whether the frequency is below 50 hertz, above 50 hertz, or the voltage is now below zero point 0.9 or above zero point 0.1. So there will be mismatch. So let's say this way. So maybe they will operate in such a way that the frequency goes below 49.5. Let's say it is now 49. They may arrive at a point where the frequency has drastically gone below our actual, or maybe we could say voltage. We had a limit of, this is 1.1, this is zero point 0.9, but due to their characteristics, what has happened is, they have now arrived at a point where the voltage is now below zero point 0.9, below zero point 0.8. But the local controllers, they are not aware that they have arrived at such points which are not acceptable. So what the secondary control layer will do, it will build upon the local control, and it will try to bring this voltage back to the acceptable limits, because here we have communication and they are aware of what the global target needs to be met. So but its operation time frame is slower than primary control, because it will only act when the primary control layer action has taken place. So this can be centralized or distributed. We'll see it in the next slides how. And since these need not be frequently operated, when we need the secondary control to action to take place, only when the local control has failed or it is not doing perfectly. Let's say the local control action took some action and the voltage is maintained between 1.1 to 0.9. In those cases, we don't need a secondary control because we are at optimal operating point within the accepted band between 1.1 to zero point 0.9. So in those cases, we don't for secondary control. Only when an unfavorable event took place, then only we will trigger the secondary control, which is now popularly known as event triggered mechanism. Then we have the topmost, that is the central. So here it is the highest and obviously it will be the slowest because it will take place after the secondary control, and it will monitor the local and secondary controllers and take the emergency action if needed, and it will set the DR set points in a longer time frame, let's say between 5 minutes or 15 minutes. And this central controller, it is responsible for, we can say, networked microgrids, a number of network microgrids, and also with the distribution system operator as we had seen. So basically it will manage the power flow, excess or deficit with the main grid. So that decision is taken by the central controller. And in case of any emergency, it will activate the emergency control procedures and it can also take some protection actions. Then we had types of secondary or central control schemes. So first one is the centralized approach. So what we do in the centralized approach is, let's say we had microgrid 1, so we have 4 microgrids, let's say, and we'll be having a central controller, right? Sorry. A microgrid central controller, MGCC. So what these microgrids will do, so they all will report to one central controller. And again, this microgrid controller, it will do some computation and it will give the new dispatch points or set points to back to the each microgrid controller. So this is how a centralized scheme is going to work, that all the microgrids are present here, they will report to one command center or control center, we can say. This then command center will do the computation and it will give back the new dispatch or new set points to the different microgrids. So the disadvantage basically here is we can have what we say single point of communication failure, because if let's say this here there is failure of communication, then all these microgrids, they will be in dark. They will not know what action to take. So that is one problem here. And here the communication is also very important. You can say for 4 microgrids we need 8 number of communication rounds, so higher communicational burden, we can say. Then secondly, we had multi-agent based techniques. So here the same thing is going to happen. But now there is no central controller. Each microgrid will talk only to its neighbor, similar to what we call peer-to-peer or P2P. So the communication here is only between the neighboring agents. And basically this will be 2, 3 and 4. So by communicating with the neighbors, this local controllers, they can achieve to the global target. With this we can say P2P communications. So here the advantage single point failure is not there, because let's say even this link fails, this microgrid can talk to its other neighbor and they can collectively achieve the global target. And this was here also the communicational burden is relieved. If you like, this was a 4 bus, like 4 microgrid system, so it was not very evident. But if the number of microgrids will increase, then you can see the number of communication rounds required between central controller, and in case of P2P, the P2P will read lesser communication burdens basically. Then moving on, we had also model predictive control techniques. So model predictive control, what we do here, let's say we have a initial state here, and we want to reach some final state in the future, which is our goal. So what control actions do I need to take? And let's say I have so I want the action to take place in 4 steps. So basically I want to go from this initial to my desired objective, final objective, by, you can say this is my final state y, this is my initial state x, and I will reach x to y using some controls, right? That is u. And that u I want to apply in steps of 4. Let's say u1, u2, u3, u4. So what model predictive control will do, it will take this initial state x, it will take this y, and it will give you the, at first let's say t equal to 1, it will give you a plan like what control actions u1, u2, u3, u4 you need to take to reach this final state. But that it not ends here. Let's say at t equal to 1 you applied this input u1, and then what will happen after applying u1, you may reach to a different output y1 which was not desired. Let's say some unfavorable condition was happening, and at the end of uh, applying first control action u1, you get y1. So what it will do here is it will again recompute at t equal to 2 now. It will consider this y1 and this final state y, and again it will give you new, I can say, a new set, like what you need to follow, that will be different from here basically. So here it will give you U2 dash, which will be different from U2, U3 dash and U4 dash to reach this final state Y, and this will go on till the last t equal to 4. So at each time instant it will re-evaluate what is the state, and then it will reach the actual final state, we can say. So this is the basic idea of model predictive control, we can say. So in the context of microgrid, basically, let's say the microgrid is at a state X, where let's say its lines have been congested and it wants to reach a final state where no congestion is there. So what the my model predictive control will do for the power system, this control action U, what are they for us? They are, we can reschedule the generators, or we can reschedule, load shed the loads. So it will give you some control actions for each time step so that the congestion is relieved. But let's say after t equal to 1, you have moved to a new state now. Let's say after t equal to 1, the initial condition has changed. Let's say a generator outage has happened or a line outage has happened. Then if you follow the same plan, you may not reach the final output, right? Because here the state has been changed. So for that, new plan has to be reformed. So that again, the model predictive controller, what it will do, it will take into account the new initial state where let's say one generator has been now out. So considering that generator outage, and again my final state as where the lines are not congested, it will give me a new set of control actions. So, and this, by this, in we can say steps, we will reach to our final goal, that is when there is no congestion. Then we have consensus based control actions. So basically we know here again we are having some privacy issues. So what data do we need to communicate among the neighbors, as I said in the P2P, that the microgrids would talk among each other, but what? They are not willing to share their own data. So what this consensus based approach will do, it will share some operations it will do. Let's say the data of mg1 was p1, of p2 of mg2 was p2, and p3 is data of mg3. So instead of sharing these variables as it is, or data as it is, what they will do is they can do, we can say they can average this out, weighted average basically, where n is equal to 3, and this information they will communicate with each other to reach the global variable. So using this consensus based algorithms, so it is a type of distributed control algorithm only, but instead of sharing the actual data, some modification is done so that privacy is preserved for those microgrids. So here we saw types of controls: distributed, decentralized, distributed, and centralized. So what are their individual features? Basically, decentralized means there is no communication. Distributed means there is some communication, and here also we can have privacy. and then centralized, which is at the top, which is looking after the, we can say, both this. So basically your local control was decentralized, your secondary control was distributed, and the centralized controller, it will look after this local and secondary, and it will give the dispatch signals at a greater amount time frame. So moving on, we'll see then here the decentralized group control for a DC microgrid. So basically now we are studying about a DC microgrid. So here we don't have frequency, we don't have reactive power. It is simple now. We have only voltage and active power. And here we can have a reference VREF, we can say. So which has to be maintained constant. And from here we'll be having different group characteristics we can have, and accordingly basically let's say we reached to a new operating point VF dash, and this is due to the increase in load, basically delta P1, and this was delta P2. So this reference here is constant. So this VF, you can say for nth distributed resource or converter or inverter. So that is VF minus, I can say, IFN and times the resistance RFN. Right. But then we have certain drawbacks here for this. So first, we'll see the case of, let's say, load sharing and voltage sharing one by one. So let's say we have a group control this way, with these kind of characteristics. Let's say I'll change here, but and another one with such kind of group characteristics. Basically here it is my V, this is my and that is my P. Okay, this was my V and this was my P. So let's say for the same voltage, we'll see how the loads were being shared in these two. So you can see here for the yellow lines, this is the delta P, right? But while for the green ones, so the power sharing is this way. So the power shared is this. So we can see from here that this is giving unequal, or we can say large delta P, which is not favorable. We want them to share equally near about. Then the same case again we see let's say now we'll see for the same power. So for here, so this was my reference. So I can see that my delta V for this is this much. But in case of this green lines, what will be my delta V? It will be this drop, which is our desirable. We don't want more voltage drop, right? This is good and this is poor. So we can see here there is a trade-off. If you are getting good power regulation, the voltage is not good, and if you are getting good voltage regulation, then they have to share unequal power sharing. So this is the drawback of this group control. So for that, what we are doing is similar to the AC control, microgrid control we had seen. There is virtual resistance method, there is group methods, and there is intelligent control methods where we use some fuzzy logic, and then we have mode adaptive group control. See here what we are doing is we are having more number of players, like there is utility, there is storage, there is DG. So in the mode 1, the utility is going to be in group mode here, this one, while the other energy storage and others, they will be in constant P mode. Similarly, in the mode 2, the energy storage will be in group mode. This is the group mode, while others will be in constant power mode. And in the third mode, the DG units will be in group, while others they will be in constant power mode. And again, moving on, here we had for DC microgrid, we had very small DC microgrid. We dispatched the resources according to their priorities using this voltage leveling method, but it had some drawbacks if we go for larger microgrids. So for that, we use the DC bus signaling method, where we dispatch the resources in form of groups. And lastly, we had power line signaling method, where we use the communications. Then we had different types of distributed control. Basically, the distributed control means where I taught you they speak peer to peer. So this methods that differ upon which type of data they are sharing basically. So if they are sharing the information of average current, so in the first method you can see among each microgrid to microgrid among them, so they are sharing the average current. That's why this is known as digital average control current sharing method. Similarly, if they are sharing the voltage, then this is the average voltage sharing method. And in the distributed cooperative model, what with control method, what they will do. So all the resources that you're having, let's say battery, let's say you have storage, so they will take the actions in a cooperative mode. They will cooperate with each other, and they will take the necessary control actions. Then we had two modes of operation for this DC microgrid: grid connected and islanded mode of operation. So in the grid connected mode of operation, basically what you will be having here is I will be having a bidirectional converter between my microgrid and the main grid. So whenever I want to power import from grid, means power will flow from grid to microgrid. So this converter, what it has to do, because our grid is AC, so the power has to flow from AC grid to DC grid. That means we will be having here inverter action, AC to DC inverter action of the bidirectional converter. And similarly, when we have excess of energy in the microgrid, we can export it. So basically energy is from microgrid to grid. So microgrid is DC, so DC to AC means we will be having rectified mode of operation. Then here we had also islanded mode of operation. So in islanded mode of operation, the microgrid can operate on its own, that is single islanded microgrid connection, or they can form a cluster, network cluster, right? And they can form multiple clusters like multi-islanded DC microgrid. So here what we can say, the reliability will be improved, the stability can be improved, there will be better utilization of the resources in case of clustered microgrids. And in case of we can say the mode of operation of the MPPT mode of operation, if we discuss here. So basically in grid connected mode, we'll operate in MPPT so that we have maximum utilization of our renewables, right? But in islanded mode of operation, we will need a battery. So battery is a must, and depending upon the SOC of the battery, we have to operate. Basically, because this battery is also having some charging discharging limitations. Let's say my SOC is below some threshold, let's say it is below zero point 0.1, means I am not having energy now. That means I have to do curtailment of loads, because I can supply power only to the critical loads. I don't have enough of energy, and in this case we can also go for MPPT, mode of operation of the renewables, because we want power here.
Madam, for power export microgrid to grid, why we are using rectifier operation? Because the grid is AC generally and microgrid is DC.
uh you're talking about this. Oh, sorry sir, I got it. Just a second. Are you talking about this, right?
Yes, on power export microgrid to grid rectifier.
Microgrid to grid, DC to AC means we have here inverter. Yeah, you were right, sir. I had. Is it fine, sir, now?
Yes,
Okay. Thank you for
ma'am.
pointing out. Yes, sir.
For grid connected operation, we can use MPPT, but for islanded, why we can't use MPPT? We are using battery.
Yes, sir. Because let's say it will depend upon my battery storage capacity. Let's say you don't have enough capacity in your batteries. We were talking about here the discharged mode. So here we can go for MPPT because we need energy. So we will try to extract more amount of power. But let's say your battery is already charged to its full capacity. The SOC, let's say it is greater than zero point 0.9. So if you charge it beyond this capability, the battery may be damaged here. So here we have excess generation. If we need to curtail them. We cannot have MPPT because if we operate them in maximum mode, that means we need to basically charge the batteries beyond this zero point 0.9, which will damage this. So for that,
Yes, sir. Yes, thank you.
okay, so for that we can't have the MPPT mode of operation in this condition where the SOC is greater than zero point 0.9. And here we'll have maximum load that can be served. Then moving on, this was the typical structure of the microgrid here. So basically you have the grid here, AC. So we have the grid side converter, which is converting this AC to again DC. Then we have PVs here, then boost converter for MPPT operation. We have wind here, again boost converter. Then we have, we can say this is hybrid energy storage, because we had seen in the previous lectures that for hybrid we take one with high energy density such as the battery, and we have ultra capacitors which are high power density, and we combine these storage technologies to form the hybrid storage. And then we have the loads connected here. So this again, this is a bidirectional converter. It can act as an inverter or a rectifier depending upon the need. Then we had moved to the AC-DC microgrid basically. So why we went from this conventional AC microgrid or DC microgrid was there, we were needing more amount of converters there, right? Because our system was AC and DC both. So then we can reduce the number of converters basically required, and there will be greater efficiency because lesser amount of converters means lesser amount of losses we can also see in the system. So we are having two types of structures for this microgrid basically. The first one is where these you can say this is one, this is second one, and both we have AC and DC sources, large sources which are of both AC and DC types. So we cannot segregate them. Like here, both the sources and loads are of AC and DC type. So if you have and we are having two buses here, one is a DC bus, one is a AC bus. So when we have a DC distributed generator here, we have DC-DC converter here. Then for the AC, we convert it to DC to connect it to the DC bus, and the storage obviously bidirectional charging or discharging. That's why here bidirectional signs are here. Similarly, for the AC bus side, we have here the AC system and also DC system, and similarly the converters here required to couple it or synchronize it to the AC bus, and then we have this interlinking converter here, which will help in power flow between these two microgrids, depending upon from like you want power to flow this way or from this way, the role of this interlinking converter is going to change. The second structure which we had was only DC loads and only AC sources. So basically here we can segregate them because in this area only we have distributed generators of DC type, and this area we have only distributed generators of AC type. So we'll segregate them, these sources and load, and this will be the DC microgrid side with the DC bus. This will be the AC microgrid side with the AC bus, and then we'll be having a converter here. So here the number of converters that is required, that will decrease from the previous one. Then operating modes for the AC-DC microgrid, which we saw, we had grid connected mode of operation, and we also saw about the why are these coming? So in the grid connected mode, we had two types: dispatched power mode and undispatched output power mode, right? So what was done in this dispatch power mode? Basically, we were having constant power mode, and this was achieved either using current control methods or using voltage control methods. And in the undispatched power output mode, there was like all were operating on MPPT, and they were just feeding it to the grid, and here we had then I-ended mode of operation. So we'll see this in detail in the next slides. So in the grid connected mode of operation, basically we saw we had dispatched mode and an undispatched power mode. So in the dispatch power mode, the interlinking, we have two types of configuration. So first one is where the interlinking converter, it will work as the, it will set the DC voltage. So basically it regulates the DC link voltage, and it works on DC link voltage regulation mode. And the other, that DGs and storage devices which we have, So they coordinate on the DC and AC bus to produce the required output power. The second type of this dispatch power mode, the DGs, the distributed generators and storage, they will regulate the DC link voltage, while the converters and other distributed generators, they will collectively control this AC bus for the dispatch of the power. So basically here the interlinking converter is working on the voltage regulation mode, but here it is working on the constant power mode, and vice versa for the distributed generators. And in the undispatched power mode, both we can say all the DGs, they will be working in the MPPT mode of operation, and the storage, depending upon the need, they will charge or discharge. And the interlinking converter, it will regulate the DC link voltage on the desired voltage, on the desired value, like the reference value basically. Then in the we had standalone mode. We want to know the role that it will, the devices like the interlinking converters, what role they are going to play in the standalone. The previous one was for the grid connected mode. So in the standalone mode, what will happen is the interlinking converter, it will control the AC voltage and frequency, while the DC voltage can be controlled directly or indirectly, because uh, depending upon the power flow of the DGs, so that voltage can be regulated. And the DGs and the storages, what they'll do, they'll regulate the DC link voltage at the reference value. And in the indirect DC link voltage control method, what will happen is, depending upon the power flow, direction of power flow, they'll regulate the DC link voltage. And here also we can have the presence of parallel converters, interlinking converters. Then we had power management strategies in case of transitions. So we had two transitions here, or transients here. One was from when we are going from grid connected to islanded mode of operation. The other was when we were going from islanded mode of operation to grid connected mode of operation. So first transient that we will be discussing here is from grid connected to islanded mode of operation. So here what we need to do is, as we know the control strategies that we need to follow in grid connected mode and in the islanded mode of operation, they are different. So this transition will require that we need to change the control strategies here. So that need to be done. So in the switch of control strategies basically, since we have different control strategies, we need to switch this control strategies whenever there is a change in operating mode. Basically here the DGs, they are working on the current control mode in the grid connected operation, while when they are going for the islanded mode, they need to go for voltage control mode. So this control switching we need to do with the help of DC-DC converters. And this can, for doing this seamlessly, we have different techniques that have been developed or that are being proposed. So firstly is we need to do this transition or this switching of this control algorithm when the line current of DG is reduced to zero, basically zero. And here what we will detect the islanding condition, and whenever the islanding detection has been done, so we will switch the control of the DGs. The next one was uniform control. So here we don't need to change the control action, whether in grid connected mode or in islanded mode, the only one control strategy is available for the DGs. So for that, the power management and control strategies, you can see they are same for both the grid connected and standalone operating modes. So you don't need any switching of control algorithms. So the smaller DGs, they will work in the MPPT modes, while you can say the larger DGs, they will operate in the voltage control mode. And how this power sharing you need to do in the during this transients is you need to coordinate the DGs to supply power to the critical loads, and for that you need to have modified group control strategies. Then moving on, the next transient was when we were going from islanded mode to grid connected mode. So basically when we have to connect to the grid now, we basically have to synchronize to the grid. So this synchronization can be done in two ways, passive or active. So in the passive way, what we do, we will continuously monitor the voltage, and whenever we see that the phase angle is matched, we will connect the microgrid to the main grid. But again, this is all, although it is very easy and practical, but what this is based on manual matching. So some voltage magnitude imbalance will always be there, and this will lead to some transients after the closing. And also it is not fast because you are not able to control, you are just monitoring something, and whenever you have the desired phase angle, then you are connecting. So basically you are waiting for the right time, that's why you can't control it. But in active synchronization mode, here what we have, so we have like 5 to 6 DGs. One DG is going to initiate the synchronization process, and basically other small distributed generators, it is going to follow the main DG, and after this the microgrid will be connected to the main grid whenever there is zero voltage crossing. So this brings to the end of this discussion of the overview of week 7. Now we'll see some questions here. So a large droop coefficient in the DC microgrid leads to less voltage deviation, large difference in current sharing, larger voltage deviation, or none of the above. Anyone? It is a DC microgrid, so basically we are having the plot between V and P, right? So let's say we have
C is the answer. C.
C, we got one C. Okay, sir, we'll wait for others. Anyone else? So, can anyone say among 1 and 2 which one is having larger troop coefficient?
Two is having large.
Which one, sir?
Two is having large coefficient.
2.
Two.
Okay, sir. Sumit, sir, you want to speak something? I think. Yeah. So basically, 2 is having larger troop. So let's say for same amount of power. So this is my reference, right? Vref. So the decrease in voltage for 2 is this, but while for 1, the decrease in voltage I can say is this much. So obviously it is leading, larger troop is leading to larger voltage deviation. And similarly we had also seen in the previous, like for power sharing. So let's see, for the same voltage it will be having, this was P. So the larger group will be having less power or current sharing. So here the answer is larger voltage deviation. Then second question, in the mode 2 of the adaptive group control, the energy storage devices and the distributed resources, they operate in which mode? Both in constant power mode, energy storage in group, and DG in constant power.
D is the answer now.
B.
Energy storage operates in group control.
Okay, so we got one B, and DG will operate in constant power mode. This is the reverse, and last one is both operate in constant current control mode. So in the adaptive group we had seen, basically sir is correct, energy storage will be in group mode while the DG is in constant power mode. While this is, which mode can anyone tell? This was mode 3.
Mode 3, mode 3.
Yes sir, right sir. And in mode 1 we had the grid in group mode and others in power mode, constant power mode. So the answer is B. Then we have the main objective of the grid side voltage source converter in the DC microgrid is to regulate the DC voltage, or it is active power balance within the DC microgrid, or it is both A and B, or none of the above.
It is it is A and B, ma'am, both.
Okay, we got one, both A and B. Anyone else would like to try?
A and B, ma'am.
Okay, we got another. Thank you, ma'am. Anyone else? Okay, the correct answer is both of you were right. It is both A and B. So the converter, it will regulate the voltage and will also do the P balance in the microgrid. The next question is, AC and DC microgrids, they are connected through interlinking converters, through cycloconverters, through DC-DC converter, or all of the above.
It is, ma'am, first interlinking converter.
We got one interlinking converter. Anyone else? I think we saw it in the slides, right? What role also it was playing in the transitional transient states. This is your ILC, interlinking converter. So the answer is interlinking converter. So that's right. And the fastest time scale of operation is for local, secondary, central emergency control, or none of the above.
Local, ma'am.
Okay, we got one local. Anyone else? So central was the slowest, right? We talked where its operation is from, we can say minutes to hours. Secondary control, we can say from seconds to minute, while the local is within seconds. The answer is local control. So next question is, which of the following do not rely on any communication for their operation? Decentralized, distributed, centralized, or none of the above?
Decentralized.
Decentralized. Anyone else? Basically, centralized control we had in the centralized or emergency control layer. The distributed control we had in the secondary control layer, and in the decentralized we had in the local control layer, where there were no communications between the controllers. Secondary, we had seen there were P2P, or there were multi-agent systems, cooperative system, and centralized also. So the centralized control can be also for secondary control also. So the disadvantages of centralized control schemes are single point of communication failure, high communication burden.
High communication burden, ma'am.
Madam, both A and B, both.
We got one.
High communication burden B.
Okay, we got one high communication burden, one both A and B. Anyone else?
Failure. Okay, ma'am. Both A and B.
Okay,
Single point communication failure will also there.
okay, sir. Thank you, sir. Yes, it will be both A and B. So we discussed here, since they are communicating to the central controller. So if that communication link will fail, then the control scheme won't work now. And we had also seen it is having high communication burden. So it is both A and B. Then we have the disadvantages of passive synchronization schemes are difficult for practical application, may lead to circulating currents, require close coordination and communication, or none of these.
C is the answer, ma'am. C.
Okay, we got one C. Anyone else?
May lead to circulating current.
We got a may lead to circulating currents. One vote. Anyone else? So we had seen in the passive synchronization scheme what we were doing. We were closely monitoring the voltage, and whenever there is phase angle matching, we were doing it manually. So it was easy for practical implementation, and it does not require any communication because we are monitoring it. But since we are doing it manually, there may be always some mismatch which will lead to circulating currents. This will be the case in case of active, where 1 dg will be in, we can say, voltage regulation mode and others have to follow it. In those cases, we need to have communication and coordination between them in case of your active synchronization scheme. But for passive, the disadvantage was may lead to circulating currents or transients. Then the power management strategies are challenged under different loading conditions due to constant power loads, voltage dependent loads, frequency dependent loads, or all of the above.
All, ma'am, all.
Okay, we got one all. Anyone else? This was the very last topic basically. It is all of the above. Basically, all these types of loads they possess and challenge to the power management strategies. Basically, this is the now. If anyone has any doubts or any confusion in any of the concepts that we discussed,
Ma'am, why we say AC microgrid? Why we say DC microgrid it is okay, but why we say AC microgrid?
because in that we are having AC loads and AC source, right?
So that is a normal grid because till now.
No, sir. Microgrid, basically the term is coming from where we are having a localized or remote application where they are forming renewables or a group of loads. They are forming a smaller micro means small amount of grid in its locality. So that is basically the concept of microgrid. Now, depending upon the type of renewables, they can be of EC or DC. But to differentiate this microgrid from the grid, so these are basically off-grid locations. So they form the microgrid.
In Indian context, I have not seen any AC microgrid.
In the Indian context, no, there, although I have not looked up to, but I may suggest that there may be in the some hilly areas where we have don't have the transmission systems networks, we can say. So let's say in those areas in off-grid locations we can have, but although I look up to it, anyone else, any doubt? This was this clear or anywhere anything?
This communication, what we are talking, ma'am, it is via the same power lines only.
It can differ, sir, not necessarily. So we have seen different modes of communication in the initial lectures, right? They were wired, they were wireless. So depending upon like how good the infrastructure has developed, so we are not necessarily like bothered about what mode we want our data to be communicated. So depending upon the infrastructure of the substation,
I think in Indian context, only PLCC is working.
sorry sir, which one?
In Indian transmission system, only PLCC is working as a communication.
PLCC we have, but GPS and all those, I'm not sure whether we are using those modes of communication right now because only smart meters are only coming up
GPS is only for the time synchronization. Only we take the facility of
for the
time
PM, yeah, for PMs.
communication. We are not taking communication as a communication role.
No, so Wi-Fi on all those, I think it will take time because now only I think Delhi has started demand response activities, and before that, battery energy storage it is coming up. And what recent developments? Smart meters are also like not like very few places. Those who are aware of net metering only those have installed in their houses. But I'm sure then these will come up in the near future.
Okay, ma'am. Thank you, ma'am. Thank you.
Thank you, sir. Anyone else? Any doubt?
Thank you, ma'am.
Okay, thank you, everyone. So, if you have any doubts, anything, so this only you need to like remember for let's say DC, it may be AC. So, this is important. If you remember these things only, that your local controller it is decentralized without any communication and it will be fastest. Then coming to distributed controller, it is secondary and centralized can be secondary control and it can be your central or emergency. And this is in the slowest time scale. And then accordingly, all other things are interrelated through this only. And basically droop only this characteristic also if you understand. So for AC, DC, hybrid AC, DC, everything will work if you understand only this droop concept. This was basically the P2P. And okay, I don't think then anyone has any doubts. But this initial, like when I was writing all this, so was this like, were you all able to get all this, or my writing was too bad to get? Actually, I needed this feedback from you. These all were when I was writing. So
बोरोडे त्यांनी चायनीजचं टाकलं त्याच्याकडे जायचं होतं इकडं हा बोरोडे या
just a minute. So was this clear, or was it too difficult to understand? Anyone, if they can like give me the feedback that Anupam sir?
Ma'am, I have not heard your question. What you said?
No, I just wanted the feedback that in the initial slides where I was like writing this way using this pointer because I don't have a stylus basically. So was it like audible, audible not? Was it readable? And
Yes, ma'am. Yes, ma'am. It is readable, and you are explaining, so it is. We are getting it.
okay, so basically I am trying to arrange for that stylus, and maybe in the next sessions we'll be doing that way, so it will be better. Okay. Okay, I think then thank you everyone. I think we'll then close this session for today.
Thank you, ma'am. Thank you.
Thank you, sir.